So, what did we learn from chapter 13? We talked about conjugated dienes, or conjugated systems, but we focused mostly on conjugated dienes. What do we know about conjugated systems? Huh? They're cool? What do we know about them?
They can add to other compounds that form carbon bonds.
We can do that. We can actually utilize them to do carbon-carbon bond formation. What was the name of that reaction? The Diels-Alder reaction, right? And we learned that we have to have a diene that is in what conformation? It has to be S-cis. So if we have a diene that's in the S-cis conformation 100% of the time, it's going to be pretty reactive. If we have a diene that's in the S-trans 100% of the time, it's going to be non-reactive in terms of the Diels-Alder. And if it can freely rotate, it's going to have to undergo that rotation before Diels-Alder reaction can occur. So we know, we called that the diene. What else? What other component did we need in a Diels-Alder? We need a dienophile, which is basically what? What was the dienophile? Pardon? Alkane? Alkene, yes. So basically an alkene, but it turns out that the alkene needs to have a substituent on it for it to work really well. Electron donating or electron withdrawing? Electron withdrawing groups, so things like carbonyls, nitro groups, nitriles, things like that help the Diels-Alder reaction because it does what to the orbitals for the dienophile? Lowers which one? The LUMO, the lowest unoccupied molecular orbital, gets lowered, and that brings it closer to the what of the diene? The HOMO, the HOMO, right? So the highest occupied molecular orbital gets closer in energy if we add electron donating groups, and the LUMO if we add electron withdrawing groups. These things get closer. And we learned that the Diels-Alder reaction allows us to make 6-membered rings, so we're making 2 carbon-carbon bonds at the same time, which is kind of neat, right? So we're able to make these rings pretty easily. We're making carbon-carbon bonds. It's an atom economical reaction because everything that goes into the reaction comes out in the product, right? So that's what we learned about with the Diels-Alder reaction. But we also learned that we can add other things across conjugated systems like HBr and bromine and other things like that, right? And we can have reactions that are under kinetic control, and we can have reactions that are under thermodynamic control. What would the conditions be for a kinetically controlled reaction? Really cold, so like minus 78, minus 100, really cold temperatures, right? And what is a kinetic controlled product? 1,2. That's right. 1,2 addition is the kinetic control, and the thermodynamic is the 1,4. And what are the conditions for thermodynamic control? Higher temperature, so room temperature or higher typically, right? Because we know we have to be really, really cold. Okay, so good. So today we're going to continue talking about conjugated systems, but we're going to move from simple systems like dienes into aromatic systems, things like benzene. And it turns out that benzene has a special delocalization of electrons, if you will, that make this thing called aromatic. Now, when you hear the term aromatic, right now, without thinking about what you've been reading, what comes to mind when you hear the word aromatic? Pardon? Rings? Okay, that would be within the reading that you're doing. But I mean, just in general, if you were out, smells nice, right? Aromatic. And it turns out that benzene does have an odor to it. I wouldn't say it's particularly pleasant. It's not something you'd want to put behind your ear, and it causes cancer. But when we talk about aromaticity or aromatic compounds in organic chemistry, we're not talking about odor. Okay? We're not talking about how they smell. We are talking about their unusual stability. When we draw their structure, it looks like we have a bunch of alkenes. But when we look at their chemistry, we don't see alkene chemistry at all. And that's kind of interesting. So there's some interesting, unexpected kind of stabilization. And benzene is one of the simplest ones of the aromatic compounds for us to talk about. So today we're going to talk a little bit about nomenclature. I'm going to leave most of that to yourself, but I'll kind of hit some high points today. We'll talk about some of the reactions of benzene and its stability. And we'll talk about the general concept of aromaticity, which applies to benzene, but actually applies to any molecule. Okay, there are a number of molecules that actually we would call aromatic. Okay, so benzene, there's the structure, right? C6H6, it's one of the simplest aromatic hydrocarbons. It is certainly one of the oldest that we know of. It has 4 degrees of unsaturation. Can you tell me where it gets all 4 degrees of unsaturation? 3 double bonds in a ring, right? So it has 4 degrees of unsaturation. And if you were just to look at this, you would go, okay, an alkene, and an alkene. 3 alkenes in a ring, right? But if that were the case, we would expect benzene to actually do addition chemistry. And what we find is that if we take benzene and we drop in a couple of drops of bromine, the bromine color stays. Bromine does not add across the double bonds of benzene. However, if I take something like ethene and I add bromine to it, it rapidly adds bromine across the carbon-carbon double bond. And I actually have a demo that I'm going to do for you on Monday that shows this. You all have done the bromine test in the lab, I think, right? And it dissipates the color of bromine, right? If you had benzene and you added bromine, the color of the bromine solution would persist, meaning that no reaction is taking place. So there has to be something special about these double bonds in benzene. For some reason, they are a lot more stable than you might expect. They don't like to do reactions. Now, that doesn't mean we can't do reactions on benzene, but it's not the type of chemistry that you think of for an alkene. Okay? Now, benzene, if you were to build a model, you would find that it's planar. All 6 atoms, carbon atoms lie in the plane. All 6 hydrogens lie in the same plane. You would have a nice flat structure. And you would also look and see at all the carbon-carbon bonds, you would recognize that they are identical in length. Okay? What's the hybridization of each carbon? Each carbon in benzene, what's hybridization? It's sp2. Every one of them is sp2. Every one of them has an unhybridized p orbital on it, right? That's why we can draw all the resonance structures for it. However, if you were to look at this structure and you would go, well, a carbon-carbon double bond should be short, right? And a carbon-carbon single bond should be a little bit longer. You would predict that benzene would probably kind of look like this. You know, kind of what, I don't know what you'd call that, kind of, I don't know. Anyway, right, it would kind of look like this structure here, where you have the short carbon-carbon double bond, the longer carbon-carbon single bond, right? Now, of course, these are exaggerated. But when we take benzene and we grow a crystal of benzene at low temperature and we do an X-ray analysis on it, we find that each and every one of those carbon-carbon bonds are identical in length. So what does that tell us? They're delocalized around the whole system, right? The double bonds are a little longer than you might predict, and the single bonds are a little shorter than you might predict. Okay? And so you have this delocalized system. And we can draw a lot of resonance structures for benzene. Okay? And so some textbooks actually draw benzene as a 6-membered ring with a circle in it. And so what you need to know is that this is equivalent to that. Okay? And a lot of times when I draw benzene on paper, I draw it that way. It's just faster for me to go, right, than it is to draw the 3 double bonds. But you need to know that those are equivalent structures. This is just telling you that those 6 electrons are delocalized throughout the entire system. Okay? So if you see it, don't confuse it. Okay? Some people think it's kind of like looking at a bolt on the end, right? Kind of is in a way. But it's a benzene ring. Okay? So if we look at the bonds, right, we would predict that a carbon-carbon single bond would be about 1.5 angstroms. We would predict that a carbon-carbon double bond would be about 1.34-ish angstroms, right? And what we find in benzene is that all the bonds are about just under 1.4 angstroms, kind of in the middle. And resonance tells us that, right? Because we can draw different resonance structures that put the electrons like this, and I can also draw a resonance structure that puts the electrons there we go. There. I just moved them around, right? So we have those resonance structures. You can see that the carbons are actually all sp2 hybridized. They do have good bond angles of 120 degrees, as you would predict. Each one of the carbons has a vacant p orbital, each one, or not vacant, a single p orbital, and each one of those p orbitals has an electron in it. And those electrons are delocalized throughout the entire system. Okay. Now, there are a couple of things that you need to know about nomenclature of benzene. Again, most of this is going to be on your own to do, but basically what you do to name a benzene derivative is you just name it as benzene with a substituent on it. So, for example, here we have a benzene ring with a ethyl group. Simply call this ethyl benzene. Pretty simple. Here we have the tert-butyl group. We would just call that tert-butyl benzene. Here we have a chloro group, chlorobenzene. If I put a bromine on there, it's bromobenzene. If I put an iodine on there, it's iodobenzene, right? Now, there are some special names that have just come through history, okay, that you need to know by definition. For example, methylbenzene, there's a methyl group on a benzene ring. Nobody calls it methylbenzene. If you wrote that on an exam, I would count it correct, okay? But nobody calls it that. We call it toluene. Does anybody know what toluene is useful for? Blowing stuff up, like TNT. You can actually make an explosive from it by nitrating it, trinitrotoluene, right? And you can make basically high explosives, okay? It's actually illegal to make TNT in the United States now. We no longer make it. There are places back during World War II that were making this a lot, and they were making it very hastily. Obviously, we were at war. We didn't have time to worry about the environment. They threw a lot of their stuff out when they were done. There are places in the United States where the ground is considered explosive, potentially explosive. It contains high levels of TNT that's been dissolved in the soil. And if I recall right, Dr. Meow actually had a research project at one time trying to detect levels of TNT in soil for that very reason. So they've been going around trying to clean this up. And World War II has been over for, what, 70-some years? So we still have areas where we're trying to do that kind of stuff. Hydroxybenzene, a hydroxyl group attached to benzene. Nobody calls it hydroxybenzene. We call this phenol. Okay? These are alcohols, but they are special alcohols. Would you expect that phenol to have a similar pKa or a different pKa from a typical primary alcohol? What is the pKa of a typical primary alcohol, approximately? 16, 17, 18, somewhere in there, right? What would you expect for phenol? It could decrease? It can decrease. And why can it decrease? Why would the pKa be lower for phenol than for, let's say, methanol? How do we determine the pKa differences without looking it up? Say if we're looking at methanol, CH3OH, versus phenol, how would we determine which one of those has the lower pKa? What would we do? We always look at the conjugate base, right? So we remove the acidic hydrogen from both of these, and we ask ourselves which one of those anions is the most stable? Which one of those anions is the most stable? The phenolate. And why is that? I can draw resonance structures. I can push the electrons from the oxygen atom of the phenol into the ring. And I can draw several resonance structures. I'm not going to draw them for you right now, but I can draw several resonance structures. So that's going to have the effect of making phenol more acidic than methanol. By a little bit or a lot? A lot. And it turns out that phenol's pKa is somewhere around 9.8 or 10. I can't remember the exact number. And methanol is around 16. That's 6 orders of magnitude. 6 orders of magnitude is it's a million. Phenol is that much more acidic than methanol because we can draw resonance structures for it, okay? Whereas we cannot draw resonance structures for the methoxide. Aniline. You could call this aminobenzene. Nobody calls it aminobenzene. We call it aniline. Aniline is a very useful molecule. It is useful in the making of artificial dyes. So many of your shirts that you're wearing right now that have a lot of nice colors with them are made possible because they start off with aniline and derivatize it and make dyes of different colors. It is a very, very useful molecule for that. Aniline is also useful in the making of a variety of pharmaceuticals, explosives. It actually turns out this was one of the derivatives that we tried to make an argument against Saddam Hussein for, that he had all this aniline around. Aniline has a military use, which is true, but it also has a lot of just non-military uses. It in and of itself is not evidence, especially in an oil-rich country where they could get these things fairly easily. Okay? If we have 2 things attached to a benzene ring, we start to have some issues. Ethylbenzene, did I put a number on that? Did I call it 1-ethylbenzene? Did I call it 1-chlorobenzene? No, because no matter which atom on benzene I place it on, it's always going to be number 1, right? However, when I put 2 things on, now I have to worry about numbers. And so here we have 3 isomers of dibromobenzene. Here I have 1,2 disubstituted, so carbon 1, carbon 2. Here I have 1,3. And here I have 1,4. Most people do not call this 1,2 dibromobenzene or 1,3 dibromobenzene or 1,4 dibromobenzene. What you will typically hear me say is ortho dibromobenzene for 1,2. Ortho means it's in a 1,2 relationship. Meta means it's in a 1,3 relationship on a benzene ring. And para means that it is in a 1,4 relationship. So I have para-dibromobenzene, meta-dibromobenzene, and ortho-dibromobenzene. And we even simplify that a little bit more by just writing O-dibromobenzene. So O means ortho, M means meta, and P means para. You know those yucky smelling cakes that they put in bathrooms? Guys, you probably know it more than, right, those little cakes that they put in the urinals and stuff, contain dichlorobenzene. That's the smell, okay? Don't know why they use it, but they do, okay? And so these types of molecules are actually very useful in a variety of situations, okay? Benzene is not the only aromatic compound, however. There are complicated aromatic compounds, and there are compounds that are actually even more simple than benzene itself. Benzene just happens to be the one that we always start with because it was one of the first ones that was discovered. This is a molecule known as benzopyrene. It is known as a polycyclic aromatic hydrocarbon, or a PAH. If you end up going to medical school and studying cancer as your research project, you will probably talk an awful lot about PAHs, polycyclic aromatic hydrocarbons, okay? The whole system is an aromatic system. But if you look carefully at it, it looks like we've got benzene rings in there, right? But it's actually one aromatic system, okay? This is what happens when you take a tobacco plant, you roll it up and you smoke it, you get benzopyrene, which you inhale, it gets into your system, your liver then oxidizes this into carcinogenic compounds, okay? And this is one of the many carcinogenic compounds that you can get from cigarette smoke, okay? So they are oxidized to carcinogenic products, okay? Some other compounds that you may be more familiar with. This molecule has 2 aromatic rings. It's got basically a ortho-disubstituted benzene ring here and an ortho-dichlorobenzene substituent here, but this is one molecule with 2 aromatic systems in it. This is known as Zoloft or sertraline, okay? It's one of the most highly prescribed antidepressive agents that we know of. It is a billion-dollar drug. Actually, it's a multi-billion-dollar drug. All the chemistry that you need to make Zoloft, by the end of this chapter, you'll know how to do. Okay. So really, a lot of the stuff that we depend on for our medicine supply really is sophomore level organic chemistry. Here we have another molecule. This one's Valium, diazepam. It's a sedative, pretty potent sedative. It has a couple of aromatic rings in it, some other groups in there as well. Novocaine. Where do you all come into contact with Novocaine? You go to the dentist, right? If you're like me, you don't like needles, right? You don't want to feel that needle go into your cheek. And so what do? They take this little cotton swab, they put this yucky tasting stuff on it, they stick it in your mouth for a while, it locally deadens it before they give you a shot. So Novocaine is the trade name, the generic name is Procaine. This is a very, very easy molecule to make. And back when I was in organic chemistry, we actually made Novocaine as one of our laboratories. They quit doing that because it's a local anesthetic, and some people are sensitive to it. Some people do have allergic reactions to Novocaine. But when you were making it, you knew if your technique was really good because your fingers would start to tingle if you weren't wearing your gloves, because it would start to have that local anesthetic effect. And it's kind of weird trying to deal with, I'm telling you because I experienced it, when you're trying to deal with glassware and you can't feel the ends of your fingers. It's kind of strange. But Novocaine is a very simple molecule. You'll see that it actually kind of has an aniline group in it, doesn't it? Right? Here is Viracept. This is a drug used to treat HIV. Again, you can see that we have an aromatic ring here. We have an aromatic ring here. Actually, this is a phenol, right? If we want to think of it that way. But you can also see we've got sulfides, we got amides, we got alcohols, we got tertiary amines, we got other amides, right? So aromatic rings with other functional groups attached to it make pretty potent drugs. Viagra, sildenafil, right? Again, aromatic ring, right? It's actually a fairly complicated looking molecule, but it's really not that hard to make. It too is a billion-dollar drug. It is called a lifestyle drug. Nobody actually needs it, but people will pay a lot for it because of what it allows you to do. Claritin, straight over-the-counter Claritin. Loratadine, this is an antihistamine. We're starting to get into that allergy season, right? Many of you will be going to the store and picking up your Claritin or your Claritin D or your generic version of it. And it is a molecule that contains a couple of aromatic rings. Here we have a benzene ring. It's actually a chlorobenzene. Here is also an aromatic ring, but what's strange about that one? It has a nitrogen in it. So a nitrogen in a six-membered ring like this, what do we call that? We've used it before as a base. Just kidding? Okay. Pyridine. So we've used pyridine before, right, as a base. It is a pyridine ring, okay? And so when you go buy your Claritin, when you're having your seasonal allergies, you're going to be ingesting an aromatic molecule, okay? Now, the thing that I've always found interesting about aromatic molecules is the fact that benzene is a carcinogen, pyridine's not good for you, and all of a sudden you start putting these things in other molecules and adding other functional groups to it, and we can treat things like our seasonal allergies, we can treat our depression, we can have our local anesthetics. So these flat aromatic rings actually play a big role in the pharmaceutical industry. Many, I shouldn't say all, that certainly wouldn't be correct, but a good proportion of drugs that we rely on are built on aromatic systems, okay? So these benzene type rings pop up an awful lot in our pharmaceuticals, okay? Now let's talk a little bit about the stability of benzene. I told you that benzene is unusually stable, and that's why we call it aromatic, right? So where does this unusual stability come from? Well, it comes from the fact that we can draw a lot of resonance structures from benzene, but how do we measure this unusual stability? Well, there's several ways we can do it. And one of the ways that we can do this is to actually do some chemistry. So let's take a 6-membered ring and let's put a double bond in it. So now we've got cyclohexene. It's one 6-membered ring, 6 carbons, but it's got an alkene in it. And if we take this and we hydrogenate it, so we put hydrogen gas in through it, we have palladium on carbon as our catalyst, right? And what are we doing to this? When we hydrogenate it, what are we doing? We're adding hydrogens, right? We're removing the unsaturation, or the pi bond unsaturation. We're adding hydrogens across the carbon-carbon double bond. Is that favorable or unfavorable? It is favorable, and we can tell that because we get energy out, right? Doing this, we get about just under 29 kilocalories per mole of energy that's released as heat when we do this, because we're going to those more stable sigma bonds, right? Okay? So what we can predict here is that the hydrogenation of a carbon-carbon single bond by itself is going to give us just about 29 kilocalories per mole. Now, if we take this same ring and we add one additional unsaturation, but make it conjugated, right, and we hydrogenate it, what we find is that we get about 55 kilocalories per mole, right? Now, if I just take this number and I double it, I would have 57 kilocalories, right? I'm not getting a full 57 out of that. Why is that? What am I losing? Am I losing or am I gaining? What am I gaining? I am gaining hydrogen. That's true, but what am I gaining overall? I'm gaining stability, right? And why am I gaining stability? More resonance structures, right? So the fact that I can draw resonance structures for this 1,3-cyclohexadiene means that I don't get the full amount of heat out. I'm only going to get 55, not 57. But this is a fairly small difference because I have a limited number of resonance structures that I can draw. However, if I take benzene and I do the exact same thing and I hydrogenate it, and I can do this. It's not easy to do, but I can do it. So I hydrogenate it with palladium on carbon. I notice that I get about 50 kilocalories per mole for the hydrogenation of benzene. 3 times 28.6 is 85. That's a huge difference. I would expect to get nearly 86 kilocalories per mole of heat out if it was 3 isolated double bonds. But all I'm getting is just about 50. That is unexpected stability. And that unexpected stability is what we call aromaticity. This is why it is so stable it doesn't want to do reactions with bromine. We can't add water across the carbon-carbon double bonds. We can't do the normal things that we can do with cyclohexene. Cyclohexene, we can add water across the double bond. We can add bromine across the double bond. We can add HX across the double bond. We can do all those things. We can do none of those things with benzene, or at least not easily. Okay? So benzene has this unusual stability that we call aromaticity. Okay? So this is just graphically showing you what I just was talking about, right? If you really thought of benzene as being these 3 isolated double bonds, we would have this structure where we had a short bond, a long bond, a short bond, a long bond, right? We would expect this. And if we were to hydrogenate this, we would get about the 86 kilocalories per mole. That's what we would expect. But what we get is this 49, and so it's this difference right here from what we would expect to what we really get. That's the stabilization energy. And it's large. Okay? And it turns out that aromatic molecules, right, have this unusual stability, and that's a good thing. If you think about your DNA bases, we'll talk about this later on. Creature dies, billions of years go by, we can take a piece of the tissue that's been preserved, and we can still analyze the DNA, can't we? Why can we still analyze the DNA? There are 2 reasons. Number 1, they use a phosphate backbone, which is very, very strong. Phosphorus-oxygen bonds are among the strongest bonds we know of. And 2, the bases are aromatic. and they hold on for a long time. It's really great that we have our genetic code stored up in really strong things, or we would be mutating all the time, right? So this concept has a lot of importance in biology, biochemistry, physiology, the whole 9 yards. Okay? So the special nature of benzene, this slide shows the difference between something as simple as cyclohexene and benzene, and this is actually the demo that I'll do for you on Monday. I will take a sample of cyclohexene and a sample of benzene, and I will add bromine across it. And you will see that as I add drop by drop the concentrated solution of bromine, the color goes away almost instantly. Benzene, I add a drop and it persists. It will persist during the entire class. No reaction will take place. Okay? But what we find is that if we take cyclohexene and we react it with cold potassium permanganate, we get rapid hydroxylation. What's the color of potassium permanganate? It's purple, right? And so when I add that to this and a reaction occurs, what happens to that purple color? It goes away. And in fact, in my lab, we use this little reaction to watch our TLC slides. So when we're running TLCs in lab, in the research lab, we have a dilute solution of potassium permanganate that we use as a stain for things that contain carbon-carbon double bonds. Because we'll take our TLC slide, we'll dip it in there, and it will turn purple everywhere except where there is a alkene, and it will turn white. And you can sit there and you can circle those little spots and know where your alkenes are coming out on your TLC slide. Again, bromine, we've already talked about that. HI, we can rapidly add across here, no problem. Hydrogenation, I can hydrogenate this easily with a nickel catalyst or palladium or platinum at room temperature, and I don't even have to be at 20 psi of hydrogen. I can just bubble it through at atmospheric pressure, and it will rapidly hydrogenate. However, if I want to hydrogenate benzene, I can do it, but it's going to be extremely slow. I'm going to have to heat it up above 100 degrees Celsius, and I'm going to have to put in 1,500 pounds per square inch of hydrogen gas to get that to go. Now, I don't know about you, but hydrogen gas at 1,500 pounds per square inch at 100 degrees doesn't sound like a fun day if something goes wrong. Okay? It's not an easy process. This, no problem. A little bit of hydrogen, room temperature, I'm not worried about it. 1,500 pounds per square inch of hydrogen gas in my laboratory, we don't do that kind of stuff. You have to have steel bombs. They actually call them bombs for a reason, right, to do this type of chemistry. Okay? And it's because of this aromatic stabilization that we have from the benzene ring. Okay? Now, that does not mean that benzene does not undergo reactions. We obviously can do chemistry with it because I showed you all those drugs that get made that have benzene rings in them. Okay? So there are certain types of reactions that we can do. What we note is that if we take a benzene ring and we add bromine into the mixture, we don't get addition of bromine across the carbon-carbon double bond. We don't get a product like this. But if we add bromine in the presence of a catalyst like iron tribromide, we do get the substitution of bromine for the hydrogen. Why might this chemistry be allowed and this chemistry not? Any hypotheses? Jack, noticing those two reactions, what might you hypothesize here?
The ion can't attack lithium electrophile because it's so stable.
Okay.
But the substitution reaction is not happening.
Okay. That is a perfectly, given the information you have here, that's a perfectly reasonable hypothesis. And it's one that we could probably test, right? And so the point is that if you look at the starting material, that's a benzene ring, right? We know it's stable. What does the product have? A benzene ring, which is stable. Have we lost our stability? No. How about up here? Is the product a benzene ring? It is not. So we wouldn't expect it to be exceptionally stable, would we? So we're losing that stabilization in these addition reactions. And so That gets to kind of what Jack was talking about. So maybe we could test that at some point. Right? Now, there are criteria for a molecule to be aromatic. You need to have all 4 criteria memorized, and you need to know that for a molecule to be aromatic, all 4 criteria must be met. So if you meet 3 criteria and not the 4th, it doesn't mean it's 3/4 aromatic. Okay? It has to meet all 4 criteria. Criteria number 1 for a molecule to be aromatic. The molecule has to be cyclic. What does that mean practically? It means if I started a carbon atom with my pencil and I trace around, I can get all the way back to the starting point without ever lifting my pencil, right? That's a cyclic molecule. Okay? So if we look at the cyclic compound here in benzene, we notice I can start here. I can go all the way around without ever lifting my laser pointer. This molecule, because there's no bond between here, this would not be a cyclic molecule. It cannot be aromatic. Even though 1, 2, 3, 4, 5, 6 carbons, 3 double bonds, everything's sp2 hybridized, but it's not cyclic. Okay? You're not going to have these orbitals overlapping because there's not a bond between here to hold them close together. Basically, this tells us that each p orbital must overlap with the p orbitals on adjacent atoms. Okay? The second rule, the molecule has to be planar in reality. I'll add that. Cyclooctatetraene. The way they have drawn it right here looks like a flat stop sign to me. So how do we know if a molecule is really planar or not? How are you all going to know? You're going to build a model. And what you're going to find is if you build cyclooctatetraene and you try to flatten it out, it's going to fight you on that. And it's going to try to bounce and form this tub shape. Okay? Cyclooctatetraene is actually a tub, not a stop sign. Okay? It has this tub shape. Because it has this tub shape, the orbitals cannot overlap. Even though it is cyclic, it is not planar. Okay? And since it is not planar, this molecule, even though every atom has a p orbital and it is cyclic, it does chemistry like you would expect. If I take cyclooctatetraene and I throw bromine into it, I get the addition product. My bromine color goes away. It does what I would expect it to do. So rule number 1 is what? It must be cyclic. Rule number 2, it must be planar. For you to know that, you need to build a model. Unless I tell you on the test, assume everything is planar or assume everything is not planar. If I do not tell you something, you need to build a model. The third rule is that the molecule must be completely conjugated. That is, they must have a p orbital on every atom. If I look at this for benzene, there's a p orbital, a p orbital, a p orbital, p orbital, p orbital, p orbital. Every atom has a p orbital. It is completely conjugated. I can draw resonance structures that go around the ring. Here, whether or not this is planar or not, it's irrelevant. It doesn't have a p orbital on every atom. This is sp3, this is sp3. No p orbitals. Likewise here, for cycloheptatriene, no p orbital. It can't be aromatic. Okay? So rule number 1 is what? Rule number 2? Rule number 3? Completely conjugated. So how I refer to it, but yeah, p orbitals on everything. You're right. Rule number 4 requires you to do a little math. It turns out the math is really easy. Okay? If you can just do a little basic algebra, you've got it. The molecule must satisfy Hückel's rule and contain a particular number of pi electrons. Okay? So if we look at this molecule, okay, here we have benzene. Hückel's rule states that you have to have 4n plus 2 equals the number of pi electrons. That's the formula. N must be 0 or a whole number. It can't be 1.5. It can't be 2.2. It needs to be 0, 1, 2, 3, 4, 5, to infinity. Okay? How many pi electrons do we have for benzene? It tells you how many do we got. 4n plus 2 equals 6. 4n equal what? 4. So n equal what? 1. Does that satisfy Hückel's rule? Yes.
What is
N is just a number. It has to be an integer. You have to solve for it. And if n is one of, if it fits that criterion, it's okay.
Okay, gotcha.
If you look at cyclobutadiene, it can be planar. It is cyclic. It is completely conjugated. It does not satisfy Hückel's rule. 4n plus 2 equal 4 does not satisfy Hückel's rule. It satisfies the 4n rule, not the plus 2 rule. Okay? It has 4 pi electrons. This is called an anti-aromatic compound. Molecules can be aromatic, non-aromatic, or anti-aromatic. What is an anti-aromatic compound? It is. That's it. It is super unstable. Cyclobutadiene has been made before at like minus 300 degrees Celsius in an argon frozen matrix. I don't remember the temperature. And it existed for a few milliseconds. You tell a chemist you can't make something, they spend millions of dollars to show that they can, and then show that it's completely useless. Okay? It is an anti-aromatic compound. It is unusually stable. Once it's made, it completely reacts with whatever it can.
Does that mean that the ring always has to be the number of carbons?
No. And we'll see some examples. It does not have to have an even number of carbons. So for example, I'll just go ahead and show you. Cyclopentadiene anion has 5 carbons and it is aromatic. It just so happens that this p orbital has 2 electrons in it instead of 1. It is cyclic, it is planar, it is completely conjugated, and 4n plus 2 equals 2, 4, 6. N equal 1. It satisfies the rules of aromaticity, and it is a aromatic molecule. Okay? This has some practicality. This table that I took from another textbook, basically n has to be 0, 1, 2, 3, etc. That gives you that you have to have 2 electrons, 6, 10, 14, 18, and so on and so forth. So we can have a lot of electrons in an aromatic system. How might we get an aromatic molecule that only has 2 pi electrons? Can anybody think of a way that we can do that? Tell you what I'm going to do. I'm going to do another little bonus opportunity for you all over the weekend. You all can figure out how to get an aromatic molecule that only has 2 pi electrons. If you get the answer right, I'll give you, I don't know, 5? I'll give you 5 bonus points that I'll apply to the exam that's coming up. Okay? So 3x5 note card, draw a structure of a molecule that is aromatic and only has 2 pi electrons. And I'll give you 5 bonus points.
But it definitely exists, though.
It does exist.
Like this isn't a trick. We spent it all weekend.
It does exist.
Structure of aromatic molecule with only 2 pi electrons.
So we will finish this up on Monday. I got to have a little bit of time to hand back your chapter 12 stuff. So I'm going to hand back chapter 12 inverted lecture. It has nothing on it. I have made my notes. You have the solutions in the solutions section of the Canvas. Over the weekend, I want you to self-grade this, make notes on it, but do not change anything. You can add too, but do not change. And then at the top, write what letter grade you think you deserve based on how you did compared to what I have in the solutions. Don't put a number, just write A, B, C, D, or F, whatever you think. Okay? I want you all to self-grade this one. So I'll call your name.